Everybody, my name is Michael Coory. This session is on statistics for public health practice, or as the subtitle suggests, it's using statistics to communicate uncertainty when, providing public health advice or making public health decisions. So this presentation is timed to go for about 40-45 minutes. It assumes that you've done at least one statistics subject as part of your MPH or equivalent. And I know that some of you will have done 2 or 3 or more statistics subjects. So look, this is not a presentation about when to do a t-test or how to run a logistic regression or how to check the assumptions of a proportional hazards model. It's about using statistics to communicate uncertainty. So just to provide some context, so you know where I'm coming from, I did a PhD in epidemiology and clinical epidemiology and biostatistics. I then did the public health exam in 2003, so I've been a public health physician for about 15 years. I've worked in universities as an academic and also worked in state and Commonwealth health departments. In state health departments, I mainly worked in the area of health systems, so funding to public hospitals, service capability frameworks for public hospitals and quality indicators for public hospitals. And then with the Commonwealth Health Department, it's mainly been health technology assessments, so subsidy of new health technology, and then more recently, I've been on the regulation side, and my current position is with the Therapeutic Goods Administration, so with the TGA in the pre-market area, so in the pre-market medicines area, so looking at the pre-market evidence for medicines and looking at marketing approvals. So what is statistics? Statistics is essentially the study of uncertainty. What is uncertainty? It's partial, limited, or incomplete knowledge. So the link between uncertainty and statistics is probability. Probability is a way that we can attach a number to uncertainty. So just some definitions before we really get going. In this presentation, I'm using the words uncertainty and risk as synonyms. Avon and Wren published a paper in 2009, and they identified 10 different definitions of risk in the literature. So risk can be whatever you want it to be. If there is an extra dimension of risk in addition to uncertainty, it's the idea of the severity of the unwanted outcome. But look, we're usually not much interested in uncertainty around outcomes that are trivial. So, usually uncertainty and risk will equate to the same thing. And certainly that's the way I'm using these words in this presentation, that they're synonyms. Now, there's other terms that sometimes used in other disciplines such as psychology or financial management, and they're terms like ambiguity or indeterminism. Look, I don't think it's very helpful to put labels on high-level abstractions. It's better to explain exactly what they are. So in this presentation, I'll only use the terms uncertainty and risk, and I'll be regarding them as synonyms. Now, this slide is the nub of the presentation. So when providing public health advice or making a public health decision, and where you need to communicate uncertainty, it's unlikely that the uncertainty could ever be reduced to one number or one probability. So it's unlikely that you could ever reduce the uncertainty to just a p-value or confidence interval. So it's better to present a set of statements of uncertainty. Now, when you're providing advice up the line, say in a health department, senior bureaucrats will often want you to give a black and white yes, no answer. P-value, does that mean, that means it's not due to chance, it's a real effect. I think it would be better to present a set of statements of uncertainty, so the full extent of the uncertainty is captured, and that is rarely captured by a p-value or confidence interval. Now, the third dot point is also important, that when communicating uncertainty, it's important to consider who carries the risk and what are their perceptions of risk. And I'll say a little bit more about that later in the presentation. So one of the premises of this presentation is that it's useful to have structured frameworks when thinking about uncertainty. So why are structured frameworks useful? Well, this is the example that's often given. So this is the Flynn effect, where this is the phenomenon that over time, so basically since the 1930s, so over several decades, IQ tests have had to be recalibrated such that the mean stays at 100 and the standard deviation stays at 15. So in other words, people are getting much better at doing IQ tests. Now, why is that? Well, it's not because human beings are becoming innately more intelligent. It's because people are much better at answering the types of questions that are in IQ tests, even though they haven't seen the questions before. And this is largely, because people have had exposure to more education these days. And so although they wouldn't call it this, it's because they have better structured frameworks for solving the types of problems that are in IQ tests that they haven't seen before. The other reference I have on this slide is a book by Dennett called Intuition Pumps and Other Tools for Thinking. So he makes the point in this book that thinking tools can make us smarter, and he draws the analogy that we can't do much carpentry with our bare hands, and similarly we can't do much thinking with a bare brain. So this presentation is going to present a structured framework for communicating uncertainty in the hope that that will lead to better decision making or advice in the presence of uncertainty or risk. So this is the framework. Obviously, to cover all areas of public health, it's very high level and broad, and consists of 3 steps. So the first step is to evaluate the p-value or confidence interval and assess whether it could be a false positive. And there's 2 sub-steps that are related, but I'm suggesting that you consider separately. So that's multiplicity and the pre-study probability. So I'll be spending the most time on step 1 because that's the most statistical step. Step 2 is to provide multiple statements of uncertainty. And I'll just spend a little bit of time on that. And then also step 3 is important to consider who carries the risk and what are their values and preferences. In other words, what's their perception of the risk. Now, right down the bottom of this slide are the unknown unknowns. Now, obviously, if they're unknown unknowns, you don't know about them. But I think it's important to keep in the back of your mind that there could be these unknown unknowns. So this is the idea of fallibilism, that everything in science is subject to revision. Everything in science is provisional, and if new evidence comes in, then then the scientific position may change. So I think it's helpful to keep, although it's not a step, I think it's helpful to keep in the back of your mind that there could be unknown unknowns, and provide advice up the line with due humility. It's also useful to think about uncertainty and have some categories for uncertainty. So deconstruct uncertainty. You can see that in this slide, I've deconstructed uncertainty essentially into 3 categories. So they're the 3 blue boxes. There are other categorizations of uncertainty that have 5 categories, so have more categories. This is a fairly simple schema that I've come up with. You could come up with your own schema. I'm not saying this is the only one or the best one. It's the one that I kind of have in the back of my mind. So if you look at the first box, so the first blue box, to consider objective statements, objective numeric statements of uncertainty. So this is basically classical frequentist statistics. So this is p-values or confidence intervals. So you can partition some of the uncertainty off into that which can be characterized or described using p-values or confidence intervals. And then you're essentially left with the known unknowns. And because they're known unknowns, you can only make subjective statements. So either you could make, this is the second blue box, you could make subjective numeric statements. So that's a very Bayesian approach. Or perhaps, the uncertainty is, a deep uncertainty that you can't attach a numeric statement to, that you can't put a number on, or else maybe you don't like the Bayesian approach and you just prefer to make non-numeric statements. So they're essentially the 3 categories. And then we have the brown box over here, the unknown unknowns. So, you know, Donald Rumsfeld was criticized by journalists, ridiculed by journalists for talking about the known unknowns and the unknown unknowns. But it's a pretty standard way of assessing uncertainty in risk management. He was just basically describing risk management 101. And then up the top, I've said, always consider who carries the risk and what's their perception of the risk. I just wanted to talk about another categorization of uncertainty, just in case you come across it. So if you were doing, say, a philosophy of science 101 subject, you would come across, uncertainty would be categorized into aleatory and epistemic. Now, I haven't used that categorization, and I'll explain why in a moment, but essentially aleatory is irreducible unpredictability or irreducible randomness, and the word itself refers to rolling a die, whereas epistemic, the word refers to knowledge, and it's uncertainty about the facts that could be reduced with learning. Now, the reason I haven't used it is the aleatory uncertainty tends to be relatively trivial, so it's not a useful category in practical terms, from my point of view. I mean, you may find it useful, but so just to give you an example, so suppose for someone my age with my risk factors, you know, there might be a study which shows that my risk of having a major coronary event in the next 5 years is 5%. Well, the 5% would be regarded as aleatory uncertainty. But obviously we would always attach a confidence interval to that or a p-value. And then there's these academic arguments about whether the p-value and confidence interval is aleatory or epistemic. Most people would say it was epistemic because you could, if you did a larger study, then you know, the confidence interval would narrow and the p-value would change. But in the end, I haven't used the category of aleatory because it tends to be a bit trivial. We're not interested in the 5% on its own, but we're also interested in the confidence interval and p-value attached to it. So that's why I've got that first category of uncertainty as aleatory plus the associated p-value plus confidence interval. Now, when thinking about uncertainty, I think it's helpful to put it in the context of the history of probability. So this is a very, very, very brief run through the history of probability. So probability, as I said, is about attaching a number to uncertainty. It was the last branch of mathematics to be developed. A lot of academic discussion about why that was the case. One reason is probably that it's not very intuitive. The other reason is probability is about making predictions about the future, and that has religious overtones. So that might be another reason why it was so late to develop. So the names I've got on this slide, Cardano was a gambler, but the other names on the slide were mathematicians who made important contributions to other areas of mathematics apart from probability theory. They saw probability as an objective measure of a physical system, and the type of physical system they were thinking of was something like a coin toss or selecting a card from a pack, or if you've done any probability theory, you know, they always talk about the urn with the black and white balls. Now, I'm sure you've seen this diagram before. This is a diagram for Bernoulli trials. So epidemiologists, as you know, like to dichotomize things, alive or dead, et cetera, et cetera. And so a lot of the uncertainty in epidemiology is modeled using Bernoulli trials. So the graph on the right-hand side of the slide is the type of graph you get if the probability is 50%. So you get a symmetric probability distribution. If the probability was 10%, say, well, then you get a skewed distribution with a long tail to the right. And if the probability was, if the outcome was rare, say 1 in 1,000, well, then you'd get the Poisson distribution, a highly skewed distribution with a long tail to the right. Now, the next step forward was due to Gauss in 1801. He became famous throughout Europe by being able to predict where an asteroid called Ceres was going to reappear after disappearing behind the sun for 41 days. So look, he had a lot of observations. He had a lot of data from astronomers around Europe, and he realized that the observations were subject to many small random measurement errors. So there were no large errors because, for example, you know, due to the telescope footings becoming unbalanced or something like that. He saw that these measurements were subject to many small random measurement errors, and you'll be able to guess what's coming next is the Gaussian or normal distribution, which we still use today as a model of random errors. Now, the next step forward was in the 1920s. Statistical inference is the process of making inferences from a small sample to a large population, and Fisher came up with the p-value, and Neyman Pearson came up with the hypothesis test. So under various assumptions, they came up with mathematical formulas to describe the variation due to finite sample size. And so today we have the p-value and confidence interval, which dates back to the 1920s. Just to say something about the confidence interval, look, it's preferred by some to the p-value because it concentrates attention on the point estimate and the precision of that estimate. But look, it essentially has the same mathematical inputs as the p-value. In other words, the formula depends on the standard error, and the standard error in turn has inputs of the sample size and the variance of the individual measures themselves. Also, there's a tendency to use confidence intervals as a pseudo-hypothesis test, in that, you know, we look at whether the confidence interval includes a null value. So for the purposes of this presentation, while recognizing that the confidence interval has some advantages possibly over the p-value, I'm essentially lumping them together and regarding them as the same thing. The other step forward in the 1920s was this idea of subjective probability. So this is due initially to Di Finetti and Frank Ramsey. So they saw that you could attach a number to expert opinion as long as the number that you attached to expert opinion obeyed the laws of probability. In other words, the number had to be a number between 0 and 1, and if you had mutually exclusive events, they had to add up to 1. So essentially, we have two types of probability. One is objective probability, so it's classical, frequentist, long-run probability that dates back to the 1600s. And it's objective in two ways. One, it's objective because we're using a model of probability based on some sort of physical system. So we're imagining that probability is like tossing a coin. It's also objective because once you agree on the mathematical formulas and the assumptions behind those formulas, then everyone's going to get the same answer. You're just plugging numbers into a formula. Whereas on the other hand, subjective probability, different experts could attach different numbers to their opinions. So objective probability, as I said, is really confidence intervals and p-values, whereas subjective probability relies on this idea of Bayesian updating. So you start with a prior distribution which reflects your degree of belief about some proposition. You then apply data to the prior distribution and you come up with a posterior distribution. And there's a whole lot of mathematics involved to make sure the posterior distribution you know, has the area under the posterior distribution adds up to 1, as probabilities have to. And then you can either get a Bayesian p-value from the posterior distribution or come up with a Bayesian confidence interval, which people tend to call credible intervals. Just a little bit on chance and randomness. So chance and randomness are very mysterious, slippery concepts. Chance and randomness probably does exist in the subatomic world of quantum physics, although Einstein did famously say that God does not play dice. But for the problems that we face in public health, chance is not really something in the physical world that we can measure. It's really just a pragmatic model for describing the accumulation of many small variations for which it's not feasible or economic or worthwhile to uncover the causes. So pretty similar to Gauss. This idea goes back to Gauss, where he just modeled the fact that astronomers in Europe were making, you know, little tiny errors in their measurement of where the asteroid was. So I've got a quote from Bertrand Russell on this slide. Probability is the most important concept in modern science, especially as no one has the slightest notion what it means. So now with that background, I'm now onto the framework or the structured framework for public health decisions or advice. So the first step, and it's the step, as I said, that I'm going to spend the most time on because it's the most statistical, is to evaluate the p-value and confidence interval to assess whether it's a false positive. And two sub-steps, that these are related, but I'm suggesting that you consider them separately: multiplicity and the pre-study probability. So first of all, multiplicity. It's a ubiquitous statistical problem. I've just given one reference on this slide that I found helpful and accessible. If you did a PubMed search or a Google Scholar search, you'd come up with hundreds of papers on statistical multiplicity. So the issue with statistical multiplicity is, as you know, p-values and confidence intervals assume one look at the data. But what if you're doing multiple looks at the data? Well, the p-value assumes that the null hypothesis, in other words, H0, is true. If the null hypothesis is true, then 1 in 20 p-values or confidence intervals will be false positives. Another way of looking at it would be to consider a logistic regression where you've got 15 explanatory variables. There's actually, again, assuming the various null hypotheses are true, then there's actually a 50-50 chance that at least one of them will be statistically significant. So statistical multiplicity is divided up into visible and silent. Visible, number known, silent, number unknown. I know visible and silent aren't the opposite of each other, but that's the jargon that's used. Now, visible multiplicities are pretty easy. So examples of visible multiplicities would be where we have pre-specified co-primary endpoints, pre-specified subgroup analyses, or pre-specified sequential monitoring of a trial. And they're relatively easy to deal with. There's statistical methods that go back several decades where we can adjust the p-value and confidence interval to account for the multiplicity. Much more problematic are silent multiplicities. Now, I've given some examples of silent multiplicities on this slide, but there's almost endless examples. But, you know, one example would be post hoc subgroup analyses where you just keep looking at subgroups in a particular study until you find one that's statistically significant. The other example of silent multiplicities is where you look at the various endpoints in a particular study and just report the one that was statistically significant. So that's called reporting bias. Publication bias is another example of silent multiplicity. So only positive studies are reported, and we don't know how many studies were done overall. In other words, we don't know how many negative studies there were. And then regression modeling is another slightly different example of silent multiplicities, where if you've done any or developed up any logistic regression models, say, you'll know that there's a lot of minor subtle decisions that are made when developing up the model, but in the paper that's published, we only ever see the final model, so we don't know how many other models were actually tested. So look, this is called p-hacking or significance questing or data dredging, and it's common not just in medicine, but in psychology and economics and sociology and various other areas of science, and it's led to something that's called the replication crisis in science. Now, the second sub-step is to consider the pre-study probability. So what do I mean by that? Well, this is a 2x2 table, which I'm sure you've seen before, 2x2 table for a hypothesis test. Now, all probabilities are conditional or contingent on assumptions. So what assumptions are is the p-value contingent on? Well, one assumption, critical assumption for the p-value, it's the only way we can proceed to calculate the p-value, is that we have to assume that the null hypothesis is true. So essentially the p-value is the column percentage. But it turns out we don't really want to know the column percentage. What we want to know is the row percentage. And the only way to get a row percentage is to make some estimate of the pre-study probability. So that's a very Bayesian approach. So we would make our best guess as to the pre-study probability, which I'm assuming would be subject to substantial uncertainty. Otherwise, we wouldn't need to do the study. So we would make our best guess as to what the pre-study probability of the hypothesis being true is. We would then collect the data, do the study, and we could then calculate the row percentage. In other words, calculate the post-study probability, or you could call it the positive predictive value. So this is very much a Bayesian approach. Now, I think perhaps the easiest way to understand a hypothesis test is in the context of a diagnostic or screening test. So the example I'm going to use is FOBT testing for bowel cancer, and this is a 2x2 table for a diagnostic or screening test that I'm sure you've seen before. So the column percentages are the sensitivity and specificity of the test, and the row percentages are the positive predictive value and negative predictive value. I'm going to focus on the positive predictive value. Now, I'm sure you've seen these examples before. They tend to be the type of examples we give people to do in ClinEpi 101. So we give people we tell people the sensitivity, 85% in this case, and the specificity, and then we say the pre-test probability is 1%, work out the positive predictive value. So in the interest of time, I'm not going to go through the arithmetic, but it turns out in this case, when the pre-test probability is 1%, given the sensitivity and specificity, which are the column percentages, the positive predictive value is only 4%. So, you know, faced with an individual patient with a positive FOBT result, and setting aside nuances around, you know, adenomas and polyps, there's only a 4% chance, so only a 4 in 100 chance that they actually would have bowel cancer when, you know, when you send them off to have the colonoscopy. So that's why, you know, this is a screening test, and it's just a way of triaging people in effect to have a colonoscopy. Now, in ClinEpi 101, we always follow up with what happens when you change the pre-test probability, in this case to 10%, but we're keeping the sensitivity and specificity the same. And it turns out the positive predictive value then increases to 32%. So look, just to emphasize the parallels between a diagnostic or screening test and a hypothesis test. So the sensitivity is analogous to statistical power, and the specificity is analogous to 1 minus the level of significance. Now, this is a table from the very famous paper by John Ioannidis, published in PLOS Med, I think in 2005. So I think it's the most cited paper in the medical literature in the last 15 years or so. I think there's been nearly 3 million downloads from PLOS Med. So the title of his paper was something like "Why Most Research Findings Are False." And so look, if you haven't read this paper, you should read it. It's an excellent paper, obviously, given the number of citations and downloads. Now, I just wanted to go through this table. Here's table 4, and maybe we'll just go through a couple of the rows. So look, 1 minus beta is the power, which has been set at 80%. R is the pre-study probability. 1 to 1 is 50%. U is a measure of bias. So U is low here. It's 0.1 because this is a randomized controlled trial. So with, you know, randomization and blinding, you know, low probability of bias. So when you do the simulations with these inputs, you get a positive predictive value. In other words, a post-study probability of 85%. So it's unlikely this is a false positive. So this is a confirmatory randomized trial. Unlikely it's a false positive. But if we go down to this row here, now the power is still 80%, but in this case, the pre-study probability is much lower. It's only 10%. And the risk of bias is higher. He set it at 30%. So maybe this is a case control study, and there might be concerns about, you know, recall bias, etc., the standard concerns with case control study. And you can see the positive predictive value here is only 20%. So quite low. In fact, there's an 80% chance the result is a false positive. And if you look at some of the other rows, you can see that there's even a higher probability that the result is a false positive. So look, you know, the paper is well worth reading. One of the examples he gives is about single food studies. So, you know, bacon causes brain cancer, coffee causes pancreatic cancer, which are never get replicated. Hence leading to the term replication bias. And this next slide is a cartoon from the BMJ from a few years ago getting at the same point. I just wanted to make the point that alpha equals 0.05 is purely arbitrary. So it was a threshold that Neyman and Pearson came up with in the 1920s. It suited the application that they were intending the hypothesis test to be used for. It was basically used as a screening test, and then you would go in and collect more data. just to say that in other disciplines, alpha is set to an entirely different level. So in genomics, where there's multiple comparisons are done on different SNPs, the p-value, or the alpha, is set to a much lower value of 0.705. And in high energy physics, they use a 5 sigma rule, so roughly 0.603. Alpha 0.05 is actually a 2 sigma rule. There is a proposal to redefine statistical significance in health to a 3 sigma rule, which would be 0.205. And there was a paper published recently, just at the beginning of this year. Benjamin is the first author, but Ian Denis is also on the paper, so that's well worth a read as well. Okay, so that's the first step, which I've spent the most time on. The second step is to provide multiple statements of uncertainty. Don't just provide a p-value or confidence interval. I just wanted to say a little bit about this step. So back to my mud map, which deconstructs uncertainty. So I've got these objective numeric statements of uncertainty, p-value and confidence interval. And then the other ones are the other category, big broad category, are the known unknowns. Now, I just wanted to make the point that the known unknowns include bias, but they're more than bias. It's bigger than bias. I'm sure you've all seen diagrams like this in Introduction to Epi courses, where they're making the distinction between bias, which are systematic or non-random errors, and chance or random errors. So look, with that mud map, the obvious question is, are the known unknowns just bias? And the answer is no. It also includes data that are just missing, and we don't know if they're biased or not. We just have no data at all. So one example could be for an oncology medicine. The first data we often get is for progression-free survival, which in a sense is a surrogate endpoint. And we have to wait a bit longer to get the overall survival, for the overall survival data to read out, because it just takes longer to collect that data. Now, we're not saying there's a bias, we're just saying there's no data on overall survival, that it's missing. Also, say for the second example there is, say for an asthma medicine, we might have data in adolescents and adults, but there's just no data in children. So we don't even have enough data to say whether there's a bias or not. We just know that the data in children are missing. So on the second step, which is consider the known unknowns or make subjective statements of uncertainty, it's more than bias. I just wanted to make the point that it's more than bias, although it includes bias. I'm going to skip over that slide in the interest of time. And then the third step is to consider who carries the risk. So there is a huge literature in psychology about people's emotional reaction to risk. So people tend to be much more concerned about risks that are, for example, man-made or out of their control, affect children, have some dreaded outcome like cancer, or are not understood. Now, that brings me, I'm just going to finish the presentation with 2 examples. Now, this first example is an example from an oncology medicine. So this is nivolumab, which is one of the new immune therapies. It's a checkpoint inhibitor, and the setting is the adjuvant treatment of melanoma. And I've given the reference to the New England Journal paper at the bottom of the slide. So the first step is to evaluate the p-value and confidence interval and assess whether it could be a false positive. Now, RFS is recurrence-free survival and HR is the hazard ratio. So the hazard ratio for recurrence-free survival is 0.65. It's less than the null value of 1, so that's looking like nivolumab is favourable in the context of adjuvant treatment of melanoma. And you can see there the confidence interval doesn't include the null value of 1, so it's a statistically significant result, and that fits with the p-value, which is 0.301, so it's about 1 in 10, it's less than 1 in 10,000. And I've given some estimates there of the recurrence-free survival at 18 months. It was 66% in the nivolumab arm versus the comparator arm wasn't placebo, it was ipilimumab, which is an older immune therapy, which is more toxic than nivolumab, and it was 53%. So nivolumab looks like it has benefits over the older treatment, which is ipilimumab. Now, if we look at the first sort of sub-step, which is multiplicities, it turns, recurrence-free survival was the pre-specified primary endpoint. So there was no sort of reporting bias or endpoint hunting there. the endpoint is okay. And then there were various interim analyses. So there is visible multiplicity coming out of the interim analyses, but they were all adjusted for with some sort of alpha spending rule. So that's fine as well. Then if we look at the pre-study probability, the pre-study probability is at least 50%. So we know that nivolumab works in the setting of metastatic melanoma, and this is just moving it up the treatment algorithm to use it in the adjuvant setting. So 50% probably about right. Most medicines that work in the metastatic setting will also work in the adjuvant setting. You know, there's occasional examples of medicines that don't. For example, bevacizumab works in the metastatic setting for colorectal cancer, but doesn't work so well in the adjuvant setting. So there is some uncertainty there. 50% is probably okay. You know, I probably put it higher, 60 or 70%, but then you get into discussions about whether there's equipoise. So let's not do that. Let's set it at 50%. And then if you crunch the numbers, the post-study probability will be greater than 90%. So step one, evaluate the p-value and confidence interval. It's not a false positive. Then if we look at step two, there's various structured frameworks for looking at step two. So the FDA and the EMA, who are the regulators in the US and Europe respectively, and you know, they're the biggest markets, probably 80% of world markets for pharmaceuticals, they have a framework. And then there is a grade framework that came out of the evidence-based medicine movement that's used for health technology assessment. And then there's lots of other frameworks, and I've just given one example there, the drug facts box from Lisa Schwartz and David Wallison. So there's various frameworks that we could adopt to help us with step two. So just to give a flavour of the sort of statements you might want to make about uncertainty in step two, first of all, we don't have data on overall survival because it's not mature. There is uncertainty about whether the benefit on recurrence-free survival would translate into a benefit on overall survival. But there are some studies on ipilimumab in the adjuvant setting for melanoma where benefit on recurrence-free survival did translate into benefit on overall survival. But there is some uncertainty there. And similarly, there's some uncertainty. In the adjuvant setting, we're concerned about quality of life because we're exposing patients to toxicity. Some of the data are missing, so that adds to uncertainty about the quality of life data. And, you know, just to give you the flavour, there would be at least several other dot points under step two. And then step three, who carries the risk? Well, that's pretty straightforward. In this case, it's the patients. Adjuvant treatment is for patients who've had all their cancer resected, and we're trying to mop up any micrometastases that might be there. So for patients with stage 3 melanoma, you know, they've probably got a 60 or 70% chance of having a recurrence within 5 years, depending on whether it's stage 3A, 3B or 3C. But certainly 3C patients would have a high probability of having a recurrence within 5 years, but 3A might not. So you would need to look at the risk of recurrence that the patient had. Not all patients would want 2 weekly Nivo for 12 months, which is the regimen. You know, it's a hard road. You know, maybe a 20-year-old might want it, but maybe an 80-year-old might not want it. So this is a preference sensitive treatment. It's really up to it's not a treatment that you would say that all patients should have. If they were being rational, that's not the case at all. It's a treatment that, you know, would depend on the patient's preferences and values, and some patients may want it and some patients may not. Now, the second example, and this is the final example, concerns a breast cancer cluster that was spontaneously reported from a workplace. So the first step is to evaluate the p-value and confidence interval. So there were 10 cases reported when only 1.6 were expected. So this gave a standardized incidence ratio of about 6, and you can see the confidence interval there. It doesn't include the null value of 1. It was standardized for age. So it's a statistically significant result with p of 1 in a million. Now, if we first consider the multiplicities are silent, so difficult to know how many there are, and they're large in number. So any one of tens of thousands of workplaces around Australia could have reported this cluster. And also there's the problem that the timing of the cluster, so the actual window basically starts with the first case and ends with the last case. So it's defined post hoc or retrospectively as well. So this is colloquially called the Texas sharpshooter problem, where the sharpshooter fires at the piece of wood and then paints the target around the bullet holes. Now, in terms of the pre-study probability, the pre-study probability is vanishingly small. So over the years, the number of causes of cancer, or the number of cancer clusters that have spontaneously reported from the community that have identified a common cause, in other words, identified a cause of the cluster, are very tiny. And there's some examples on this slide. So although the p-value of 1 in a million looks impressive, it's probably a false positive. So if we go to the next step, making subjective statements of uncertainty, there are protocols for investigating clusters as there are with investigating new medicines. So I'm not going to go through it in any detail, just to give you a flavour of what might occur in step 2, or the sort of steps or the sort of statements you might make. So look, the risk factors that we know of for breast cancer are pretty weak. And so, some of the women at the site had some very weak risk factors for breast cancer, such as delayed childbirth, or they did shift work. But essentially, the 6-fold increase in risk couldn't be explained. The only way to explain it was to say that it was a chance event, which is not a very convincing or compelling explanation. So for this example, probably the most important step is step 3, who carries the risk? So obviously it's the women employees who carry the risk. It's a dreaded outcome, breast cancer, particularly in premenopausal women, but also obviously also in postmenopausal women. And it couldn't be explained. It wasn't understood at all. Certainly couldn't be explained by the risk factors, by any characteristics that the women had. So look, the decision was made to close down the workplace, and I think that's a defendable decision. I don't know whether it's a right decision or a wrong decision, but it's certainly defendable, and I think it's defendable in the context of step 3, is that it wasn't understood and couldn't be explained. Now that's the end of the presentation. I'll just leave you with the structured framework, and look, thank you very much for your attention.
Are you okay, Michael?
All good at this end, yep.
Perfect. If you just have a look at the chat function down the bottom of your screen, we just have a little message there for you.
Okay, hang on, I haven't got anything. So that'll be is that the top?
At the chat function.
Okay. Yep.
If you hover over the bottom of your screen.
Yes. Is anyone here? Yep. I don't think there's any questions. So unless anyone has. Brittany, should I ask if people have questions, or can they? People still on the line, or?
People are still on the line, and they can definitely hear you.
Okay. Hi everybody. Does anyone have any questions or would like to make a comment? So Brittany, I think that's a no.
Oh, we do have one that's just come through.
Okay. Do you recommend any specific textbooks to learn more about this? Look, there's a site, David Spiegelhalter, who's a professor of risk communication in the UK, has a website which has quite a lot of good information. I can't think of any specific textbook, but David Spiegelhalter's website is really useful, and he's a Bayesian statistician, but he's done a lot of work in medical areas and in health. So his website is good. He's also published some papers that explain risk, and I've included a couple of them on the slides, they would be a good starting point. So that's what I'd suggest. Start with his website, and also with a couple of his papers, which I've included as references on the slides.
Does anybody else have any questions before we let Dr. Coory go for the afternoon? If we have no more questions, thank you so much, Professor Coory, and we'll see you shortly.
Okay, thanks, Brittany.
Have a great afternoon.
Yep, you too. See ya.
Bye.
Bye. Bye.